All right, this is Chemistry, Unit 4, Part 1, Atomic Theory and Structure. If you're dividing your notes up for how we'll take notes in class, you should start with a single piece of paper for this actual unit. For this part, you should divide the front into 4 sections, which have models, scientists, atomic theory, and parts of the atom. Again, remember you can pause this video and set up your notes any way you like. Then you should flip that page over if you're dividing it into sections as I have it done, and that would be atomic number, mass number and atomic mass, then isotopes, and finally just extra information. You might run out of room in certain squares, so this would be where that extra information could go if you run out of space. So we have our earlier models of the atom, and John Dalton came up with the very first one, which he really just said it was a billiard ball, and so he thought it was just a solid sphere. Before him was Democritus, and Democritus just thought it was a speck. So, he didn't really even give it a shape or anything. But then after him, J.J. Thomson came along and came up with what we call the plum pudding model, or the chocolate chip cookie model. And he thought it was primarily just a sphere of positive material with negative material just dotted throughout it. It's called plum pudding because plum pudding is a lot like, just to give you a visual, it would be kind of like vanilla pudding with raisins in it. So that's kind of what the raisins would be, the negatives. Okay. Then Rutherford had the model that there was a nucleus. And really, I always have called this one the planetary model because it's just like the planets spinning around the Earth, or moons spinning around the Earth. So Rutherford just really had the idea that there was a nucleus and then that the electrons spun around the outside of it. And then there was Niels Bohr, and he modified Rutherford's model, and he actually said that the electrons travel in specific pathways. This one's sometimes called the planetary model as well, but I typically call it the orbital model. Okay, so you can see it both ways, and I do give credit for both ways when we are asked about the models. And then the last one is the most modern, and it's the quantum mechanical model, and it was done by Heisenberg and Einstein and Born, not Bohr, but Born, but they actually came up with the fact that electrons didn't really travel in pathways, but more like in clouds. So Democritus came up with the first model, and he goes in your scientist section, and this was around about 400 BC, and he was the first person to come up with a theory that everything was made up of little particles, and he called them atoms from the word atomos. And he said that atoms were indivisible and indestructible, and that they made up everything. The one thing that was bad is he couldn't actually prove it. In his time period, it just wasn't available for him to, with the technology in it that he had, to be able to actually test it and prove it. So his theories kind of weren't well known. Aristotle came along after him and did some, and had a little bit more ability to kind of prove it. So he actually got Aristotle thinking about it. But John Dalton, who came along in 1766 to 1844, he was an Englishman, and he's generally the one that's given credit for the first experiments to prove the nature of atoms. So if you think about it, we went from 400, 300 BC all the way to 1766, right around the 1800s, I will tell you, before actually experiments were able to be done to prove atoms existed. His experiments resulted in what we call the atomic theory, and there were 4 specific points to the atomic theory. So John Dalton should be under your scientist, and Democritus should be under your scientist. You could also have Aristotle under your scientist, and Aristotle would come in between Democritus and John Dalton. So John Dalton's atomic theory had 4 major points to it. And the first one was that he said that all elements are composed of tiny, indivisible particles called atoms. The second part of Dalton's atomic theory said atoms of the same element are identical to each other, and the atoms of any one element are different from those, are a different form than those from any other element. So they're specific, kind of like our DNA is specific to us. Atoms are specific to an element. Point 3 in Dalton's atomic theory said that atoms of different elements can physically combine with one another in simple whole number ratios to form compounds. Okay, you'll never see H2.50, okay, because that's not a whole number ratio. They'll always be put together in whole numbers. That's why your subscripts, when you see compounds, are always a whole number, because you can't do a fraction of an atom. And then chemical reactions occur when atoms are separated, joined, or rearranged, but the atoms of one element are never changed into atoms of another element as a result of a chemical reaction. Now, when we talk about nuclear reactions, that won't be true. But for Dalton's atomic theory, the thought was that atoms are never changed into atoms of another element just because of a chemical reaction. They're changed into a different form because we can join them, or we can rearrange them, or we can separate them, but we're not actually creating new elements, okay, or new atoms. So that is the atomic theory, and that is Dalton's atomic theory. We'll talk about how that theory's changed a little bit in what is now more modern, but those are the 4 points that you need to have written down. And I will remind you, you can rewind this, you can pause it to make sure that you have that written down in your atomic theory section. So then, a definition of an atom, and this should be in your parts of an atom square. So the atom is the smallest particle of an element that retains the properties of that element. So, and we can go through these and actually figure out how many atoms are each of these compounds. So in CO2, which is carbon dioxide, we've got 1 carbon and 2 oxygens, because that subscript 2 means there's 2 atoms of oxygen. So that would mean that it actually has 3 atoms. And then H2O, we would have 2 hydrogens and 1 oxygen. So that again would also have 3 total atoms. And then H2SO4 is actually sulfuric acid, and that has 2 hydrogens, 1 sulfur, and 4 oxygens, which would give you 4, 5, 6, 7 atoms total. Now, after Dalton, like I said, much of his theory still stands, but some of it has changed. The one change that you will be aware of is that atoms are known to be divisible now, okay? But that is the one thing about his original theory that you should know, is that he said that the atoms were indivisible, okay? But we do know that they can be broken into smaller parts now, okay? We will learn about those smaller parts and 3 subatomic particles that it can be broken down into, and that's still a part of the atom in your notes. So in the structure of the atom, we have an electron. And an electron is a negatively charged subatomic particle. Really, they have a -1 charge, and they are 1 over 1,840th of the mass of a hydrogen atom. That means a hydrogen atom is like 1 AMU or 1 gram, okay? And so since it's really tiny, because you can take that and divide it by 1,840. So it's super small. The other thing to realize is its actual mass, grab my thing, I don't have it memorized. Okay, so when you write an electron, you would write it as e to the -1, right there, e to the negative. Its mass is actually 9.11 times 10 to the -31st kilogram. All right, and its charge is hold on. Okay, so its charge is actually -1.6 times 10 to the -19th coulombs. Okay, these 2 actual pieces right here, the mass and the charge were developed by Robert Millikan, which is another scientist on another slide here in a little bit, but so I'll come back to it. All right. But again, an electron's negatively charged. It's a little tiny particle. It's outside of the nucleus. That's also something you might want to write down. And it was actually discovered with something called the cathode ray tube. Okay, and that was just a device that created charged particles. So this is what a cathode ray tube looks like, and it creates a charged particle beam, and that beam can get deflected, and because it's deflected downwards, that means it's getting it wants to go away from the top plate up here, which is negatively charged. So this right here is negatively charged, so it moves away from it. So these must be a negative charge. Okay. So it got deflected towards the positive plate, and that's why it's a negative charge, because opposite charges attract and like charges repel. So J.J. Thomson is one of your scientists. So again, in your scientist square, you need to make sure that you understand that he was credited with the discovery of the electron. He did use a cathode ray tube. Okay, he found that the ray did move from the negative to the positive. So he proposed that the ray was composed of negatively charged particles, and he then called them electrons. He also calculated the charge to mass ratio of the electron, but he doesn't actually get that credit for that. He gets the credit for discovering it, but he was actually just a part of helping to calculate the charge to mass ratio. Okay. Now Robert Millikan, who was actually the scientist in 1916 who actually gets credit for the properties of the electron. Okay, so Millikan and J.J. Thomson actually were scientists that didn't work together, but he gets the credit for the charge again, which is negative 1.6 times 10 to the negative 19th coulombs, and he gets the charge for the actual mass and proving that those values were correct, which is 9.11 times 10 to the negative 31st kilograms, which is super tiny. Okay. Now E. Goldstein discovered the positively charged particles in the cathode ray tubes. So he did say there were, J.J. Thomson said there were negatives, but Goldstein said, hold on, there can also be positives. And so these particles were later called protons, but E. Goldstein kind of gets the credit for discovering those protons. So protons are your positively charged subatomic particles, and protons are noted as a P positive. So E. Goldstein goes in your scientist, and protons go in your parts of the atom. They have a mass of 1.67 times 10 to the negative 27th kilograms. And believe it or not, their charge is exactly the same as an electron, but it's positive. So it's positive 1.6 times 10 to the negative 19th coulombs, which makes sense because when you put positive protons and negative electrons together, they become neutral, and that's because they have the same value of charge. All right. Now, a neutron was discovered by James Chadwick, so James Chadwick needs to go in your actual scientist part. He discovered it in 1932, okay, and part of the reason that the neutron was discovered is because there seemed to be this missing mass, and all the protons couldn't account for the missing mass, and the electrons were so tiny that they couldn't account for the missing mass. So there had to be a particle that didn't affect the charge and how the actual atom interacted, but it did affect the mass, and that's what James Chadwick discovered. Okay, he discovered that they have about the same mass as a proton. So that would mean that their mass was 1.67 times 10 to the negative 27th kilograms, roughly. Okay. He also did realize that they were located in the nucleus along with the protons. Okay. And then he also realized they didn't have any charge. Okay. I do have some videos embedded in here that if you watch the PowerPoint, you can actually just click on them. They're on YouTube, and you can watch them. So once the subatomic particles had been discovered, like the protons, the neutrons, and the electrons, Dalton's model of the atom had to be modified. It wasn't a billiard ball anymore. Okay, and so the first model that was proposed after these discoveries was J.J. Thomson's plum pudding model. And like I said, he thought it was positive material that then just had negative electrons inside of it. Because remember, he's responsible for discovering electrons. So he didn't know anything about the positive part of it. So that's where the plum pudding or the chocolate chip cookie model came in. All right. Rutherford then got credit for the nucleus, though, because he discovered J.J. Thomson, or he looked at J.J. Thomson's model and went, something's not right. And so he actually did his gold foil experiment. And in his gold foil experiment, he shot alpha particles at gold foil. Alpha particles are positively charged. And so some of them went through. And so if they had all gone through, then then it couldn't have been positive material because those positives should have repelled each other. Well, some of them did bounce back. So he was like, there must be a positive location, but the whole thing's not positive. So his experiment really allowed us to see that there were densely packed centers in atoms that were positively charged, and that most of the atom was really just empty space. That's what Rutherford's experiment really told us. So he does get credit. So Rutherford's another one of the scientists you need to put in there. He gets credit for the discovery of the nucleus. The prevalent thought before this was that J.J. Thomson's model was correct and that it was just mostly positive substance with negative electrons throughout, like vanilla pudding and raisins. But Rutherford sought to prove this wrong, and like I said, he shot alpha particles through gold foil onto photo paper. He expected to see the particles go through with very little deflection, but what he saw was that some particles went straight through, but some bounced back, and some actually just had deflection. So he was like, something's not right there. So like I said, he shot the beta particles, or the alpha particles, and then some bounced back, which would be these right here. They bounced back. Some went straight through, but some actually got deflected, which meant that things, as the alpha particles were hitting, if they hit the solid center, they bounced back or off at an angle. If they went through, then they didn't actually hit anything. And so that's where we came up with most of being empty space. So the nucleus is one of those parts of the atom again. It's the central core of the atom, and it's made up of protons and neutrons. It accounts for almost 99% of the atom's mass, which makes sense considering they have the same mass and they're so much bigger than electrons. The nucleus is also positively charged because if it only has positive protons and neutral neutrons, then positive's the charge it gets. Okay. Now the atomic number is the number of protons in the nucleus, and this is on the back side of your notes if you're doing them divided the way I had them. But the number of protons in the nucleus, and when you look at the periodic table, the atomic number is at the top. And so I recommend also that you have a printout of the periodic table. I have posted one on my Google Classroom that you can print out, and I recommend that you put on the top legend that the top number of the squares is the atomic number. And I recommend that you go ahead and put with that protons. Okay? So what's the atomic number of the following elements? Aluminum, if you look it up on the periodic table, is 13. Carbon on the periodic table is 6. Bromine on the periodic table is 35. Iodine is 53. Sodium is 11, and I think that's silver, Ag is silver, is 47, okay? All right, yeah, 13, 6, 35. Again, just look at the top number of the squares. So if I ask you how many protons are in each of these as well, you should be able to tell me the same, because the atomic number is the number of protons. All right, so what element has the atomic number 32? Look it up on your periodic table. It should be germanium. How many protons does helium have? Helium is atomic number 2, so it has 2. What element has 79 protons? Well, the element that has the atomic number of 79, which is Au. What is uranium's atomic number? Uranium is down at the very bottom of your periodic table, and the number at the top of its square is 92. How many electrons does... I don't want to touch my recording because if I touch that, and I don't remember what that one is. So, but I will tell you, I'm going to go ahead and just say that it says, I don't know, let's say it says sodium. I don't know if it says sodium or not, but sodium is atomic number 11, which means it has 11 protons. So if I was asking about how many electrons it has, it should have the same number of electrons as it does protons, because it is a neutral atom. Okay, so as long as they're neutral atoms and everything that we're talking about in this unit is, they'll have the same number of electrons and protons. So if we're talking about sodium, it would have 11. But again, I don't remember what that says. So. All right, mass number. This is a new square. The mass number is the number of protons and the number of neutrons in the nucleus added together. So mass number would be protons plus neutrons. All right. Isotope is another one of your squares, and you need to write this actually down. Atoms that have the same number of protons, but a different number of neutrons. The easiest one for most people to remember is carbon, and there's a carbon 12, and there's a carbon 14. And those numbers, carbon 12, that means its mass is 12. And carbon 14 means its mass is 14. Well, the only difference in those two, they're both carbon, so they both have 6 protons, but carbon 12 has 6 neutrons, and carbon 14 has 8 neutrons. And so the only difference between those two is their neutron value. So these numbers right here are their mass number. So if I ask what is the number of neutrons in each of these isotopes, we would look up the atomic number on the periodic table, which for aluminum it is 13. So we just really subtract those two numbers, and we'd end up with 14 neutrons. Okay. Then carbon is 6 on the periodic table, so that would be 6 neutrons. And then bromine is 35. So we would end up with 5 and 4, yes. Okay, neutrons. And then iodine is 53. So we'd end up with 74 neutrons. And sodium is 11. So we would end up with 12 neutrons. And Ag is 47. So we'd end up with 61 neutrons. Okay? So I just subtract all those. How many neutrons are in potassium 39? Well, potassium is 19 on the periodic table. So if I want to take neutrons, I would do my mass number minus my protons. So my mass number here is going to be, you could also say it is your mass number minus your atomic number. That means the same thing. So here I have 39 minus 19, so I'd have 20 neutrons. How many protons are located in lead 208? Well, lead is Pb on the periodic table, so that would be 82. And if an element has 22 protons and 26 neutrons, what is its mass number? Okay, it would be, its mass number would be 22 plus 26, which would be 48. And what element is in the previous question? We'll look up the number of protons. And number 22 on the periodic table is titanium. Okay. So this I'm going to leave this one. We're going to skip past these. Okay, atomic mass also needs to be written down on your periodic table or on your notes. Now, atomic mass is different than mass number. It is a weighted average mass of the atoms in a naturally occurring sample of an element. Now, atomic mass unit is defined as 1/12 of the mass of a carbon-12 atom. So those need to be written down as definitions. But there is a difference between atomic mass and mass number. Atomic mass is a weighted average. Okay, the weighted average. Whereas mass number is just adding the protons and neutrons together. So if I have a sample of cesium and I have 75% 130 cesium-133, 20% of cesium-132, and 5% of cesium-134. To calculate its average, I would take all my percentages and put them in decimals, multiply them actually by the mass values, and then I would take all those values and add them up. That would create 132.85 AMUs. Those AMUs, I would then look on my periodic table, and my periodic table has that mass as, that's an average atomic mass on the periodic table as well. So the calculated value is 132.85, which I just found. And on the periodic table it says 132.905. So it's pretty close. So those are pretty accurate doing it that way. Okay? And that ends part 1, and part 2 will be in a separate recording.